Hello everyone. Welcome back to this lecture series on Design of RCC Structures. This is lecture 14 in which we are going to discuss the design of staircases using limit state method. So far we have discussed the design of beams, the slabs using the limit state method. In today's lecture we will study another important structural component used in the buildings called the RCC staircase. We'll first understand the basic concept and loading on stairs, and then we'll go through a complete numerical example on the design of a waist slab type staircase as per IS 456. A staircase is a structural element that provides vertical circulation between the floors, and it transfers the load safely to the supporting beams, slabs or walls. In reinforced concrete construction, staircases are usually designed as slabs which are spanning between the supports and then subjected to dead load, live load and finishing load. Structurally, a staircase behaves very similar to a slab, but the load calculation differs due to inclined geometry. The staircases are designed as slabs, but loads are calculated carefully considering the slope and step geometry. Let us now understand the loads acting on a staircase, which is a very important part of stair design. It starts with the dead load components. The dead load consists of the self weight of the waist slab, self weight of the steps in case if it is a waist slab type staircase, and the weight of floor finish usually between 0.5 and 1 kilonewton per meter square. The live load on the staircases as per the loading code of IS 875 part 2 will be taken as 5 kilonewton per meter square for general staircases, whereas for residential buildings with low crowding it will be considered as 3 kilonewton per meter square. In stair design, both the dead load and live load are significant and must be carefully evaluated. Why so it has to be carefully evaluated is here the slab orientation is inclined, not horizontally as like the conventional slabs. So in that case, if I want to find out the self weight of the slab means, we'll use the relation the thickness of the slab into unit weight of the concrete. Whereas this one will give the value which is perpendicular to the axis of the slab. But in this case, the axis of the slab is an inclined one. So whatever we are calculating the self weight by using this relation will be acting perpendicular to the axis, which is an inclined one. But normally, if you are designing the reinforcements, the moment calculations in which the load should be considered vertically. So that is why this load has to be converted in the vertical direction. Therefore, we are using the relation W is equal to WS into root over R square plus T square divided by T, where R represents the rise and T represents the thread of the steps. In other words, if the inclination of the stair is known, theta is known means, we can use a relation Ws into secant theta also for converting the inclined load in the vertical direction. Regarding the types of staircases, in general we have three major classifications, that is the waist slab type, thread riser type and isolated thread slab type. Here the steps will be provided over a waist slab which is of a rectangular shape. That is called the waist slab type staircases. Secondly, we have a thread riser type in which there won't be any waist slab will be available. The steps will be provided with using the RCC itself. And the third one is isolated thread slab type in which there won't be any riser will be considered in the form of an RCC. There will be a gap which will be provided between each steps. So these are the three major classification which will be used. And regarding the plan, we are having the going in which the steps are provided, and on either side of the going we are having the landings. So here the landings may be in the form of either it may be a slab, landing slab, or it may be a landing beam. So in both the way it can be connected. Now if you want to find out the effective span of the staircase means, we'll use the relationship going plus half the width of the landing on either side. That is what has been given here. The effective span will be equal to G going plus X plus Y, in which X and Y, in any case, it should not be exceeding 1 meter. If it is exceeding 1 meter in the sense, that value will be taken as 1 as such. And regarding the types based on the configuration of the staircases, it has been divided as stage stairs, in which the flights will be provided in a single direction. Second one is the quarter turn stairs, in which the flights will be provided at a 90-degree inclination. The third one is the dog-legged staircases, in which the flights will be provided at a 180-degree inclination. And finally, the open well staircases, in which the flights will be provided at a 90-degree at all 4 directions. In addition to this conventional staircases, we are also having a special types of staircases called the spiral stairs as well as the helicoidal stairs. Let us now move to a numerical example. We are required to design a waist slab type staircase which consists of a straight flight of steps supported between 2 stringer beams on either sides. The given data are effective span is given as 3.5 meter, riser 150 mm, tread 270 mm, and it has been supported with a live load of 5 kN per meter square. Here the materials used are M20 grade concrete and Fe 415 grade steel, and the slab or the staircase is to be designed for mild exposure condition. So this problem is very typical of staircases used in public or commercial buildings. As with slabs, staircases are governed by deflection control. We assume span to depth ratio of 20, hence the overall depth or the thickness of the waist slab will be calculated as 3500 is the effective span divided by 20, you will be getting 175 mm, approximated to a value of 180. Now adopting the overall depth as 180 and assuming a clear cover of 20 mm with a main reinforcement diameter of 12 mm, the effective depth of the slab can be calculated as 180 overall depth minus clear cover and minus half the diameter of the main reinforcement. You will get the effective depth as 154 mm. Here the depth assumption is the first step and must satisfy the strength as well as the serviceability requirements. Now let us calculate the loads acting on the inclined slab. Starts off with the self weight of the slab, which is on the sloping direction. That is here the overall depth, that is the thickness of the slab into unit weight of the concrete, which will give the self weight of the slab as 4.5 kilonewton per meter square. And you know this load will be acting perpendicular to the axis of the slab. Here in this case, the slab is an inclined one. Whatever this value is being calculated, which is acting perpendicular to the axis of the slab, that is 4.5 kilonewton per meter square. And this has to be converted in the form of vertical load, for which we'll use the relationship Ws into root over R square plus T square divided by T, in which Ws represents the load which has been calculated perpendicular to the axis of the slab, that is 4.5. And R and T represents the riser as well as the tread of the steps respectively, which has been given as 270 mm and 150 mm respectively. So substituting all the values, we will be getting the load on the horizontal span in the vertical direction as 5.15 kilonewton per meter square. Next is the weight of one step. Here the profile of a step will be in the form of a triangle. Therefore, the load, if it want to be calculated, means the area of the profile multiplied with the unit weight of the concrete. That is half into, this is breadth into height. Here breadth represents the tread, height represents the rise, and this one is the unit weight of the concrete. So multiplying these values, you will be getting the dead load for one step. It is not per meter, it is per step, exactly speaking. But we are supposed to calculate per meter length. Therefore, the load of steps per meter length will be 0.51 divided by how much distance that value will be acting is for the tread distance. That is what? divided by 0.27. Now we are converting in per meter length. That is why it has been multiplied with 1. So I'll get the value as 1.89 kilonewton per meter square. Now the live load acting on the slab has been given as 5 kilonewton per meter square, and the finishing load has been assumed as 0.6 kilonewton per meter square. Now summing up all the red highlighted loads will get the total service load as 12.64 kilonewton per meter square. So for getting the ultimate load or the factor load, the load factor will be multiplied with the service load of 12.64. We'll get the factored load as 18.96 kilonewton per meter square. Here the loads are calculated per meter area of the staircase. Now, moving on with the bending moment and the shear force calculation. As this slab is resting over on simply supported ends, the maximum bending moment will be calculated using the relation W L square by 8. Here W is calculated as 18.96 and the effective span is 3.5 meter. We'll get the maximum bending moment as 29.03 kilonewton meter. And this has to be checked with the limiting bending moment case of 0.138 FCK BD square, in which FCK is 20, B is the width of the slab. In that case, we are assuming 1 meter and D is being assumed as 154 mm. So substituting all these values, we'll get the limiting bending moment as 65.45 kilonewton meter. Now checking these two cases, we can see that MU is less than MU limit. Therefore, the section will be treated as an under-reinforced section. As you know, if it is an under-reinforced section, it is having the advantages like the member will behave as a ductile one. It will also shows visible cracking before it is getting failed, and it is economy comparing to the over-reinforced section. Therefore, under-reinforced sections are preferred in practice. The maximum shear force will be calculated using the relation WL by 2. So substituting the values of loads and effective span, we are getting the maximum shear force as 33.18 kilonewton. Now once the bending moment is known, we shall move on with the design of reinforcement. As it has been designed as a one-way slab, the main reinforcements will be provided in the shorter span direction. Taking the consideration of Annex G 1.1b for under reinforced section, using the relation mu is equal to 0.87 Fy ASTD into 1 minus Fy AST divided by FCK BD, substituting the moments, and B is 1 meter with an effective depth of 154, we are calculating the AST as 566 mm square. And this AST has to be checked for the minimum AST condition of 0.12% of the gross cross-sectional area. Here the gross cross-sectional area is, this is 1 meter length and this is capital D, overall depth of the slab. We are getting that value as 216 mm square. And the calculated AST is greater than the minimum requirement of 216. Therefore, we can provide the reinforcement for this AST of 566 mm square. Since already the diameter of the bar has been assumed as 12 mm, the spacing of the bar will be calculated as 199 mm. That is area of the one bar divided by area of the steel required into 1 meter. So I will be getting the spacing as 199 requirement. Now we are providing 12 mm dia bars at 180 mm centers as main reinforcement. And don't forget, this spacing has to be checked for the maximum spacing condition of 3 times the effective depth, and in no case that the spacing should exceed 300 mm. So here the 3 times the effective depth will comes as 462 mm and the maximum condition is 300 mm, whereas we provided is 180 mm. Therefore, the assumed spacing is satisfying the maximum condition. Therefore, the slab is safe against the cracking condition. Now we'll move on with the design of the distributors. And as you know, it has been already discussed that the distribution reinforcements will be calculated based on the minimum percentage of the reinforcement that has been calculated as 216 mm square. So assuming 8 mm dia bars, the spacing of the bars will be calculated as 232 mm. Here AST, small AST is the area of one bar, that is pi by 4 into 8 square divided by the area of the steel required is 216 mm square. Now the distributors is being given with a maximum spacing condition of 5 times the effective depth or 450 mm in whatever the case. So we are getting the 5 times the effective depth is 770 mm and maximum spacing is 450 mm, and therefore the calculated spacing is sufficient enough. Since this is less than the maximum spacing, therefore provide 8 mm dia bars at 220 mm centers as distribution reinforcement. So once the flexural design has been completed, we are moving on to the shear design, in which the nominal shear strength will be compared with the permissible shear strength and to check whether the shear reinforcements are required or not. Starts with the nominal shear strength, which is using the formula VU by BD, substituting the value of the shear force of 33.18 kilonewton divided by B is 1 meter and small d is the effective depth of 154 mm. We are getting the nominal shear strength as 0.22 Newton per mm square. And this has to be compared with the tau c value, that is the permissible shear strength, for which the percentage of the tension reinforcement to be calculated, that is 100 AST provided by B into D. So here the AST provided is 629 mm square, B is the width of the slab, that is 1 meter, and D is the effective depth 154. We are getting the percentage of the tension reinforcement as 0.41. And from table 19 of IS 456, for M20 grade concrete as well as the percentage of tension reinforcement as 0.41, we are getting the tau c value as 0.44 Newton per mm square. And this is the permissible shear strength in the concrete. Now it has been seen that this tau c is, it's not less than, it is greater than tau v. That is nothing like tau v is less than tau c. That is, the calculated nominal shear strength is less than the permissible shear strength, and therefore shear reinforcements are not required. Next, moving on with the reinforcement details, we can see the effective span is being given as 3500 mm or otherwise 3.5 meter. The tread is given as 270 mm, riser of 150 mm, and the main reinforcements is being provided as 12 mm dia bars at 180 mm centers and the distribution of 8 mm dia bars at 220 mm centers with a base slab thickness of 180 mm. Here, the nosing of the bars, the nosing of the steps can also be provided with the bars of 8 mm dia, and the steps bars, in order to have a monolithic casting of that is steps as well as the slab using 6 mm dia bars at 150 mm centers. So this is the reinforcement details for the slab whatever been designed. Now let us summarize today's lecture. Staircases are designed as inclined slabs. Load calculation is the most critical step, as the slab is in an inclined manner that has to be converted in the form of vertical loading. So the base slab type staircases carry slab weight, step weight as well as the live load in addition to the finishing load. So the design includes flexure, shear as well as the serviceability checks. So proper detailing ensures safety and durability of the structure. Thank you.